双击哦。
我不确定我有到。
我几乎不跑到那边。
那就不用。
我最近都乖乖的挪到这里。这另外一个是梦梦给你的。
对。
这个。
对。我有2张，那个我不确定。
几乎一样啊。
型号也是一样。
型号不太一样，因为你那个是蓝色的，这个是白色的。现在这个都买不到哎。
为什么？我们那
大家都要。
很久以前买的。
我也是很久以前买的。
对啊。
现在真正网络的需求性太高了。
为什么呢？因为他们说有一些课老师规定就是视讯，就上课的时候用Zoom要开视讯，然后因为有些学生他会想要睡着，他就把视讯关掉，然后他就等于缺课。所以很多学生他就要去买那个网络摄影机，如果他不是用笔电的话。对。
手机不是也可以有镜头吗？
对，可是会太热，因为说2个小时。
对。
对啊，所以有一些课它就是规定大家全部都要开视讯。
对，所以我们考试也是要开视讯的，确保他们没有作弊。只是礼拜三还要做一次演练。不然我那边 OK 了吗？
可以。
可以。你目前网络摄影机是刚刚好到那一个边，可以 cover 到这边吗？
现在就是这样子，只有那边没有而已。
OK。现在线上观赏的人有超过10个嘛？
我看一下。
礼拜三好像都特别少。
礼拜三特别早。看一下连续。现在好像还没有人。
没有人。不过我相信你礼拜三8点钟的session会
应该
爆了。
大家的。
为了成绩还是比较在乎一点。
现在有4个人。
4个。好。不错。 start our class. Today we're going to talk about electric potential, right? So the first thing, I will give a definition to electric potential, and then I will explain its physical meaning in details. Then we are going to derive the electric potential due to a point charge, a discrete single charge, right? And then we can use that result to expand, and we can have the information for whatever distribution of charge you have. You can have multiple discrete charges, or you can really have continuous charge distributions. Then I will talk about the strategies in finding electric field intensity, the general rule, and then we can talk about more details about electric dipole, right? So, the definition of electric potential actually starts from one of the null identities we covered for vector analysis. If you still remember, well, examination is coming in 1 week, so this is a good chance for you to review the covered topics. So if you have a scalar function, you perform its gradient, and then you perform the curl. By definition, it will become 0. We talked about this physical insights. If you perform the gradient to a vector, to a scalar function, it will be normal everywhere, right? So if you have the vector is normal everywhere, you perform its closed loop integration, curl, you don't have any net circulation. So the definition of electric potential is really closely linked to this null identity and the second postulate we made for electric field intensity. We assumed E fields are conserved fields. If you have a conserved field, its curl must be 0. Right? So if you compare this, the second postulate, to the null identity, curl of a conserved vector field must be 0. And null identity tells you curl of a vector is equal to 0. If the curl of that given vector is equal to 0, that vector can be represented by the gradient of a scalar function, right? So we compare these two directly. Now we can say E, our E field, which is a vector, because its curl is equal to 0, we can write E in some form as the gradient of a new scalar field. So our E field can be defined as the gradient of a scalar field. And that scalar field is called the electric potential. Right? So basically these two are closely related. A conserved vector field can be written as the gradient of a scalar field. They are both functions of position, right? But one thing you note, one thing very special is I have added a negative sign to it. So actually, the E field intensity as a function of space is the negative of the gradient of the electric potential, also a function of space. So think about it. Why am I adding that negative sign? What's the importance of the negative sign? Alright, so let's come to the blackboard. Assume I have two planar charge distributions. We already went over planar charge distribution. You know how to calculate the resulting E field intensity. So in this case, I have one planar charge with positive charges. The second one is having negative charges. All right? Due to a planar charge distribution, we have constant E field intensity. So I can quickly draw the field lines for you, right? The electric field lines starts from a positive charge and ends on the negative charge. So in this case, all I have to do is draw the electric field lines. So these are my E field lines. Okay, it starts from the positive charge and ends up on the negative charges. The next thing I want to know is, well, somehow the electric potential is a scalar function. It's not really having direction. But after you perform the gradient of it, then you have a vector. So vector comes with amplitude and direction. So fictitiously, if I can draw some lines, right? So these lines are somehow perpendicular to my electric field lines. So I can somehow say, oh, I have potential A and potential B, right? So on this yellow line, on this point, this point, this point, they should have the same potential. And on this point, this point, this point, as long as they are on the same line, they have the same potential B. Right? So now is a decisive point. If you were to compare the potential between A and B, which one is having a higher potential? Think about it. Electric charges with positive sign usually are taken as the ones having higher potential. This is like the mountain, and this is like the valley, right? The height of the mountain are usually taller than the valley. So it's our custom to define the positive charges are having higher potential, right? So in another way, you can understand it as the field lines start from the location with higher electric potential and ends up at the locations with lower electric potential. Okay? So this point is having a higher potential as compared to this point. The next question is, so that we know V is increasing as you walk from the negative charge towards the positive charge, right? As you can see, the direction of increasing V is anti-parallel or reversed direction as compared to the E field lines. So what about gradient of V? Gradient of V comes with an amplitude and a direction. Now refresh your memory. As we covered about gradient, by definition, gradient points in the direction where you have the maximum increment of that scalar function. So when you have gradient of V, it also points to the left. Right? This is the direction where you have the increasing electric potential from the negative charge towards the positive charge. So your E field is from the left-hand side to the right-hand side, from the positive charge to the negative charge, but gradient of V is in the reverse direction. It points from the negative charge to the positive charge. This is the direction where you have increasing electric potential. Okay? It's in the reversed direction where your E field is pointing to. So this is why we have to include the negative sign. Right? So this is just a mathematical definition, but the mathematical definition with or without the negative sign, it can all hold. But to make it physical meaningful, to our understanding, positive charges are having higher potential as compared to the negative charges. So we need to add this negative sign to take into consideration that del grade V is pointing in the reverse direction as compared to the E field lines. All right? Again, the physical meaning. So you have a lot of electric field lines. So the physical meaning of electric potential is, well, if you have a charged particle sitting somewhere in space, you have electric field intensity distribution, and you move the charged particle along a certain path, you need to contribute work to it, right? So suppose in this case, we have a charge, particle, and if we take that charge and we start from location B and we move it to point A, how much work do we need to put in so that this charge can be successfully moved from position B to position A? That amount of work divided by its charge is your electric potential, right? So the amount of work done in moving a charge from one location to the other divided by its charge, by definition, is your electric potential, right? Again, E equals negative grad V also tells you if you have a charged particle, if it moves along the electric field line, you lose electric potential, right? So if you have a charged particle sitting somewhere here where you have the higher potential, it moves in the direction of your electric field line, right? Along it, you lose potential. So in this case, you don't have to devote work. You actually gain some energy, right? You don't have to give the energy into that particle. That particle loses potential, so somehow you gain energy. So this is again the same thing, but viewed from a different perspectives. Right? Okay. So this is in the differential form. So if you know electric potential as a function of space, you can perform the gradient and remember to take the negative sign, then you arrive at the E field intensity as a function of space. In the integration form, if you already know the E field intensity profile, and you want to know how much energy difference or potential difference you're having when you move the particle from point 1 to point 2, you perform the line integration and you take the negative sign. That's your potential difference. This is your work, right? This is your work. And work divided by that charge gives you the potential difference. Okay? So, are we clear from the audience? Are there questions from the audience? Right, so basically I spent a lot of time telling you why the negative sign is necessary. Okay? Because due to the fact gradient of V is pointing in the direction where you have positive changes in that scalar function. But the E field is pointing in the direction where you have negative changes. So they are reversed. Okay, so you have to take account of that negative sign. Right? So let's take a look at the problem. We have a single charge, right? Single charge with amount of Q. We already know the E field intensity distribution for a single charge. That's from Coulomb's law, right? Q divided by 4 pi epsilon 0 r squared. R means the distance from my observation point to the charge. If we want to find the potential of a single charge, remember, the previous equation tells us the absolute value of the electric potential is really arbitrary. Okay? What we care about is the potential difference between the 2 points. So whether this is 5 volts or this is 10 volts, it doesn't matter. All we care about is their difference. So for a single charge, we can define a reference potential. And usually we want to have the reference being set at infinity. Meaning we're very, very far away from that point charge. And that's where we define the potential to be 0. Okay? For r equals infinity, we define its potential as 0. So as we move from a very far position and we walk towards the charge, we have, well, if it's positive charge, we're increasing our electric potential. So we can use our known fact. For a point charge, you have radiant, E field line distributions. We can just insert that into the equation and we perform the line integration, right? So in this case, a point charge resembles its fields, resembles a sphere. So we are using spherical coordinate. In spherical coordinate, as we change its radius, its dl, differential length, is simply r unit vector times dr, right? So this differential length making a dot product with an E field that is also pointing in the R direction, you can perform its direct integration. So basically, for a point charge, it sets up a scalar electric potential as a function of distance as its charge divided by 4 pi epsilon 0 r. So it's inversely proportional to r only. As compared to E fields, it's inversely proportional to the r squared, but E fields are also vector. Potentials are only scalar. Right? So this is coming from direct integration to our basic knowledge, our understanding, to Coulomb's law. Now we know the electric potential of a single charge. We can expand our knowledge. So if we have lots and lots of discrete charges, they all have different spatial location, all you have to do at any observation point is to sum them up. The procedure is identical to what we covered for E field intensity. But the only difference, if you compare finding the potential, total potential, due to discrete charge distributions, as compared to the same charge distributions, but you're trying to find the E field intensity. For E field intensity, you are analyzing vectors. So you have positions and you have a more complicated spatial dependence, right? Look at the potential. It's a scalar. So the only thing that matters is the distance and the sign of the charge, right? So the conclusion is, for the same problem, well, finding electric potential is easier because you're only dealing with scalars. If you were to find E field intensities, you're dealing with vectors, okay? More difficult. All right, so we can expand from discrete charges to continuous charge distributions. That's also fine. For potential, all we have to do is we expand from summation to integration. If you have value charge distribution, surface charge distribution, line charge distribution, it really doesn't matter. All you do is sum them up. If you really have continuous distributions, you perform integration. You have discrete charge distributions, you just perform summation, right? So this is a general guideline. Eventually, if you want to understand everything, ideally, we need to understand the E field intensity, right? It's a vector. But somehow, up to now, we have learned at least, well, 3 methods to find out the E field intensity. The easiest one is given by Gauss's law. So in the future, whenever you receive a problem or you want to study certain case, if Gauss's law, right, you only have to form a closed surface and you count for how many charges you have within that closed surface. That's what Gauss's law tells you. So whenever you have good symmetry, you can find a way to form a simple closed surface. Use Gauss's law to find out the resulting E field intensity. If your problem does not give you a lot of easy access to symmetry, the easier way is find the scalar electric potential first. Why? take a look. Finding the potential is usually much easier as compared to finding the vector E field intensity. Okay? So what I'm proposing is, if you cannot or you don't know how to invoke Gauss's law, for sure, try instead to find the electric potential. Being a scalar is easier to analyze. You have less chance to screw up, right? So once you have derived the scalar electric potential as a function of space, then you perform its gradient, and remember, please remember to add the negative sign. And then you have the proper expression for the electric field intensity. Okay? So the strategy is, if you can use Gauss's law, use it. If you cannot, you're not certain, try to calculate the potentials instead. It's like a byproduct. Easier, but it can also give you the final result. So if in some cases you don't know how to invoke Gauss's law and you don't really know how to calculate the scalar electric potential, then just use Coulomb's law. Okay? That's your final strategy, your only way. Just do it starting from raw, step by step. Okay? Use Coulomb's law. But usually, if you don't know how to invoke this one and you don't know how to calculate this one, your certainty, your chances of getting this right is really not that high, right? Think about it. This is like philosophy. If you can use the easiest method, use it. If you cannot, use the second easiest and use the hardest. What are your chances of getting the right answer using the most difficult method? Low. Okay? Think about it. So, just try to convince you. I am going to walk you through a simple example. It's example 3-9 in your textbook. So we are going to calculate, well, eventually we want to know the E field intensity. But first, let's try to calculate the scalar electric potential first, and then perform this gradient. All right? So now we have a uniform charge distribution in a disk. Okay, so charges are uniformly distributed over a disk. So you have rho s, which is a constant. It's not position dependent, right? Charges are uniformly distributed on this disk. And this problem wants to know, if I have an observer on the z-axis with certain distance, what is the resulting E field intensity? But first, let's try to look for the electric potential first, because potential is scalar function. All right, always, before we begin, before you write down the equation, don't rush. As I mentioned time and time, over and over again, when you take a problem, the most important issue is you are being able to identify which one of the three orthogonal coordinate systems is most beneficial for you. In this case, the geometry we're trying to analyze is a disk, right? A disk. A disk can be most easily described using cylindrical coordinate system. Okay? So we want to use cylindrical coordinate system for this case. decided to use cylindrical coordinate system, then each differential surface in this case is pointing to what direction? This is the point where you really need to think. Currently, the problem is spelling out the differential surface for you, this filled pink area. So this differential surface is actually pointing in the z direction, right? So your differential surface is the one pointing into the z direction, so dsz. As I mentioned repeatedly over and over, if your area is in the direction of z, then its magnitude, its area, must be determined by the differential length in r and phi directions. Okay? So this is again where you have to remember, in the phi direction, because your unit vector is an angle, so this differential length is in fact an arc length. So you have to have r d phi. And again, I'm using the prime system to denote the charge coordinate. Okay? All right, so the area is pointing in the positive z direction, but its magnitude, the area, is defined by dr prime times r d phi prime. Okay? For each differential surface, its center to my observation point, I must know its distance. And that distance is easy, right? This is 0, 0, z. The observation point is somewhere on the z-axis. So that distance is z, and this distance is r. So basically, r prime squared plus z squared, and you take the square root, and that is my proper expression for the distance. Right? Then we can just put into the integration form. Electric potential as a function of z, because I limited my observer to be on the z-axis. There is no x, no y allowed, only z allowed. Okay. So rho s divided by 4 pi epsilon 0, and then this is my r, my distance r, and this is my integration of the entire surface. It's a scalar treatment, much, much friendly as compared to vector analysis, right? Okay, so this phi, the hypotenuse angle, you have to integrate from 0 all the way to 2 pi. And luckily, in the integrand, we have no phi dependence. So that gives you a direct multiplication of 2 pi, right? 2 pi. So all we have to integrate is in the radial direction from a radius of 0 all the way to b. The radius of this disk is b. Okay? So do you know how to perform this integration? I hope so. It's straightforward. Okay? So take a look. There's one small trick. One small trick. If you want to derive the proper answer, you have to note your observer can be anywhere on the z-axis. So this z value can be positive, meaning you're above the disk, but you can also be below the disk, where z is negative. So whenever you work on this problem, be careful. You have to take consideration into the z location is the value being positive or negative. Okay? So why do I need to add this absolute value sign to Z? Let's try to analyze this. If I draw the cross section, so this is my disk, and this is my z-axis. Okay? Somehow we know I have charge distributions, and I assume I have positive charges. So somehow, this is my potential. So the potential needs to decay, right? As I move away from the disk, the potential decays. Okay? If I move away in the direction along the positive z-axis, it decays. Now what happens if I move along the negative z direction and move away from the disk? It also decays, right? This should be symmetric. By that reason, you must have this minus and the absolute value. Otherwise, if you don't have the absolute value, when your z is negative, negative, negative becomes plus. So it means if you don't have the absolute value, your electric potential is increasing as you move away from the disk in the negative z direction. So that cannot be true, right? So although the mathematical derivation is simple and straightforward, you can just perform the integration, but in the end, you always need to understand the problem in a physical sense. If you have the charges, you move away, you expect to have a decay in its electric potential. It has to decay when you move away in both directions. So how can you properly formulate that fact? Using math, you have to add this absolute value sign, right? Okay, so now we have the mathematical formulation for V. It's a scalar. We can perform its gradient and then add a negative sign to it to find the corresponding E field intensity, a vector. So in this case, even though, so again, do you still remember the proper formulation for gradient in cylindrical coordinate? If not, go back and study, because next Monday you will be using it. Right? In this case, we're lucky, we only have to perform the z differentiation, because the entire scalar function is only z dependent. So you only have to perform the z differentiation. And for cylindrical coordinate, r and z, you're lucky, you don't have to add the Jacobians. Okay? So basically, you can just directly differentiate electric potential in the z direction, right? Again, pay special attention to the directions, okay? When you are above the disk, you have one way to express the resulting E field distribution. When you're below the disk, you have to make proper changes to truthfully reveal that the fact is, if you have positive charge distribution of rho s, then your E up and E down are having different directions, right? Field lines start from a positive charge that emit in a radiant pattern. So when you are above it, your direction is pointing up. When you are below it, being radiant, right, outward, you have to have a flip sign. So that's the reason why when you are below it, you have a negative Z pointing, E field intensity. So the trick is, in dealing with electromagnetics, you have to understand about the signs of the potential, the directions of the fields. All right? It's extremely crucial. An easier way to express this rather complicated result is you use the sign of Z. Right? So where Z is positive, this gives you positive 1. Z is negative, it's negative 1 to take account into that negative sign. Right? Take a close look at our result. You can take this one. Right? Forget about the sign. Have we derived this previously? Is this entirely new? Do you still remember what we concluded in last class? If you have a planar charge distribution, do you still remember what type of E field intensity does it contribute to? It's a constant, right? If you still remember, if you have a planar charge distribution, it sets up an E field intensity which is constant, does not decay when you change your distance. So in this case, you have the distance dependence in this term, right? In the second term. But in the first term, you have 1. The first term is not distance dependent. So somehow this is telling you this disk geometry, when you make certain approximation, it will become the planar charge distribution that we analyzed. In that case, we assume the plane is infinitely large. Okay? So how can we make this disk with a finite radius to appear as infinitely large? Think about it. This is where my job really comes out. 2 seemingly different examples. But if you're willing to change and challenge yourselves, make approximations, the 2 problems become the same. So if the observation point, the Z value, is very small, so you're trying to evaluate the E field intensity very close to the disk. When your Z is very, very small, you're very close to the disk. This B relatively seems to be very big, right? So if your B to Z ratio is really huge, like beyond 10, 100, this term can be dropped. Why? Because B is much, much greater than Z. You don't care about this term, and because B is much, much greater than Z, you don't need to care about this term. So if B is reaching to infinity, or another sense, you are very close to this disk. Your E field is pointing in the Z direction, and you have the sign of Z to reflect its true direction. But the magnitude is rho s divided by 2 epsilon 0, which is identical to what we covered. right? Do you want to go back to where we covered the disk? No, the plan. Just to remember this one. Rho S divided by 2 epsilon 0. Identical. Right? So two similarly different examples. If you are willing to challenge yourself and ask yourselves a certain extreme number, they become the same. Okay? Here you have derived using Gauss's law, so the E field intensity is pointing in the z direction with the right direction included by the sign, but the magnitude is a constant, rho divided by 2 epsilon 0. Here you see the same thing. Even though you change the geometry of the charge distribution into a disk, but as long as you're very close to that disk appears like an infinitely large plan. Therefore, the answer should converge to what you have derived previously. And that is truthfully revealed here. So if B, the radius, is going to infinite, meaning you have a very big disk, the second term can be dropped, and your result converges to what we derived previously. Right? So I know time is not exactly up. We are 5 minutes early, but let's take a recess. So we take a 10 minutes rest, and we will come back to the analysis of electric dipole in more details. Right? So let's take a rest. So now let's take a look at electric dipole again. This is the second encounter to electric dipole. Again, I'll walk you through the definition, and this time, let us try to derive the electric potential of an electric dipole and somehow use that potential function to calculate the electric field intensity. The whole purpose is to justify, if you have a more complicated problem, trying to calculate the scalar potential and then perform the gradient is an easier approach as compared to calculating the direct vector electric field intensity. Okay? Again, if we have two charges with the same amount of charge but different in sign, and they are somehow separated by a distance d, that is an electric dipole. Di means you have two, okay? Dipole. This is the result that we derived on your slide number 15. Somehow using Coulomb's law and using approximation, where your observation point is very far away from the dipole, we have this result. So my main purpose now is to calculate the electric potential of the dipole, take its gradient, and show you can arrive at the same result. When we calculate the electric potential, remember, the potential is a scalar and is only 1 over r dependence. So everything is much more simplified. So the distance from the observation point to the positive charge is called r plus. The distance from the observation point to the negative charge is called r negative. So that's what I have 1 over r plus minus 1 over r minus. Here you have a minus sign because this charge is having a minus sign. Now, because we're still trying to assume our distance is very far away from the dipole, so basically r plus, this r plus, right? This r plus is r. R is my position relative to the origin in the spherical coordinate system. Okay? So r plus is r minus d divided by 2 cosine theta. R minus is r plus d divided by 2 cosine theta. So using that information, we can directly have the approximation of 1 over r plus and 1 over r minus. So these are just math, and you have the PowerPoint in front of you, so I can go faster. But just by doing that, okay, just by doing that, you quickly arrive at the potential as a function of distance due to the presence of these two charges forming an electric dipole. Super quick. Because you're dealing with scalar function, you don't really have to deal with the directions, the unit vectors. Okay? Okay? This is minor. I can just jump. So again, this is what we derived. Now we have the proper formulation to express the potential as a function of position. But in the end, we still want to know the E field intensity. Okay? So all we have to do is perform the gradient, and don't ever forget to take the negative sign. So this is the moment of truth. Have you understood gradient for all three different orthogonal systems? For spherical coordinate system, in the theta direction, you need to divide it by r. Okay? So why is gradient for this case only r dependent and theta dependent? You don't have the phi dependence. You don't have to perform the phi differentiation. Because in our current case, when we're far away from the dipole, we only have theta dependence and distance dependence. In the phi direction, everything is uniform, okay? Okay, so you can just have this result. Okay? So as I simplify, I have the E field intensity due to the dipole. It reads QD divided by 4 pi epsilon 0 R cubed. But now I have these two contributions. Okay? Now if you compare that to what we derived on slide 15, they should be identical, right? Aren't they? Aren't they supposed to be identical? But somehow, the result we got from Coulomb's law is having R dot D times R vector minus D vector. And then compared to the result we have now, derived from the potential burst, and then making the negative gradient, they don't really look similar. So let's take one step further. Let's try to analyze it. This P, okay, we can always define the dipole moment itself being a vector. It's in the z direction because now we have the dipole aligned in the z direction. You have the charge and you have the distance. So basically, dipole moment is nothing more than the multiplication of the charge multiplied by the distance. And now you have a well-defined direction. Direction is defined as from the negative charge pointing towards the positive charge. So this is D vector. Okay? So Q times D vector is your dipole moment. This is your dipole moment. Z unit vector, how to change this Z unit vector into spherical coordinate system. That's what we covered in vector analysis, the first PowerPoint set for vector analysis. Z can be interchanged to R and theta. Right? So this is just a coordinate transformation from the Cartesian coordinate into spherical coordinate system. Now, Q times D vector is just your P vector. So basically, R dot D times Q is R dot P. Right? Whenever you have two vectors making dot product, you have their magnitudes multiplied together, and then you have the cosine theta. So basically, we can somehow change what we arrived using Coulomb's law, right? We express it, and we rearrange it, okay? Just by defining the dipole moment. And magically, that result is actually identical to what we are having now. Okay? So a lot of mathematical equation, take your time and read on your own. What I'm trying to say is, although we're using two different approaches, One is using Coulomb's law. We derive directly for the E field intensity. What we're trying to do now is we start from deriving the scalar electric potential, and then we take its negative gradient, but the results are identical. But the truth is, using the potential approach is easier and straightforward because you're dealing with scalar functions, right? So this is not my intention to cover the mathematical derivation. My intention is to show you the result of the electric dipole. Electric dipoles are so important to our understandings to electromagnetics, right? So this is what we have from the textbook, figure 3-15. It's showing you when you have a positive charge and a negative charge with the same magnitude, but only difference in the sign, and they are somehow spatially distanced by d. This is all these circular structures in the solid lines are the electric potential being set up by these two charges. On the other hand, the dashed lines shows the resulting electric field intensity. So these are the E field lines. So try to compare, I mean, in your heads, or you can just draw it. Again, if we only have a single charge, how does the E field lines look like? When you only have a single charge, if you have a positive charge, all the field lines emit from the charge and going out, right? It's a radiant. And we also know that if we have a single negative charge, all the fields are terminated onto the charge, also in a radiant or sun-like fashion. But the importance of having the dipole is to bring these two charges together, right? So if you have this single charge, you know it's a radiant, sun-like field distribution for each one of them. But now you bring these two together. So when you bring these two together, for example, I have the negative charge here. So I'm going to use a different color. Okay? The white means originally for each single charge, you only have a single charge, you have a radiant pattern. But when you have the second charge having the negative sign but equal charge amount, you form an electric dipole. In this case, there's only one single E field line that remains unaltered, unchanged. That is this line. By definition, E field starts from the positive charge and ends up at the negative charge. So this is the only line that remains unchanged. For all the other lines, you have to have some kind of variation, right? Fields still emit from the positive charge and ends up at the negative charge, but they're somehow bended. All these other rays, they cannot be a single straight ray. They are all bended. I don't have a big board, okay? Okay, you have rays coming out extremely far away, right? So this is what this plot is showing. Truthfully, right? After our analysis using Coulomb's law or using the electric potential and then you perform the gradient, doesn't matter. They all give you the same result. And through that, we understand, oh, all the field lines are now somehow distorted, right? When you have multiple charges, the field line distribution and therefore potential and electric field intensity are no longer that simple. They are no longer sun-like, but they are somehow, use your imagination. This is actually three-dimensional. So if you have a three-dimensional plot of the resulting E field lines, what does it look like? For Taiwanese students, we don't like to eat this type of food, but for Western friends, this is what you might eat every day, like a donut. We do have a Mr. Donut just across from our the main gate of our campus, right? So as I said, the entire thing is phi symmetric. So you can take this single cross section, you rotate around this z-axis, everything will be the same, and therefore you have this donut. So along it, you have the E field lines. You have donuts of various sizes. Okay? Oh, the way I'm plotting is somewhat rotated 90 degrees. Okay. But take a close look and ask yourselves, do you understand what are being plotted for you? You have your voltage, right? So here, you have a closed solid trace, meaning above the positive charge, you have positive electric potential. V is also called voltage. So potential equals to voltage. So when you are above, you have positive potential. When you are below, you have negative potential. Why? In spherical coordinate system, cosine, right? When you are above, theta takes on the value between 0 and pi over 2. Right? Therefore, cosine is positive. So when you are above, cosine is positive. When you are below, your theta value is between pi over 2 to pi. You have negative cycle. Right? So what happens when you are on the intersecting plane between the two charges? What I'm asking is, this is d over 2. This intersecting plane equally distanced between the two charges. What should the resulting voltage or potential be? To the left, you have positive potential. To the right, you have negative potential. So exactly on the bisecting plane, your potential needs to be 0. Cosine pi over 2, 0. Okay? So at this bisecting plane, you have potential 0. Above it, positive potential. Below it, negative potential. What other special aspect do you notice? Everywhere in this figure, the solid lines shows the equal potential contour. So try to link that to how I introduced gradient. This is is like the height of the mountain, right? So gradually this is lower potential and we are walking towards higher potential. Everywhere, the E field lines, the dashed lines, are perpendicular to the equal electric potential contour. Why? Come on, because it's by definition. Because E field intensity is defined as the gradient of V, right? So everywhere, your E field line must be pointing perpendicular to your electric potential. But the direction has to be, the E fields has to point into the direction where you have potential reduction because you have a negative sign. Okay? So by looking at this plot, in the direction of E, you're losing electric potential. So basically, the outer lines, the outer solid lines shows you where you have the lower electric potential. So as you walk into the direction or against the direction of E field line, you gain potential, right? So this is the importance of the dipole. We like to use the dipole to show you that when you have multiple charges, you are actually synthesizing more complicated E field distributions. But the dipole is a very good starting point to understand such synthesis, right? But once you master Gauss's law, Coulomb's law, there's no problem. You can just do the derivation, okay? Point by point, we perform the integration. So I know I have the next slide for the students, but I prefer to wait. So I will introduce the electric dipole for the third time near the end of the semester. So I'm closing the first PowerPoint set here. I want to reserve the next slide for until the end, right? The reason is we have these two charges separated by D. But in this case, we're talking about a static case. So all you see is this beautiful graphs. But when you allow these two charges, the distance can be allowed to change as a function of time. Then you have a time-dependent electric dipole. Then you have the ability to generate waves. But I want to reserve that until the very end, when we talk about time variation of fields. So are there questions? Otherwise, I am going to close the first PowerPoint set. Static electric fields in free space. I am going to stop here. Any questions from the students? No? All right, so let's move on to the second PowerPoint set. As I mentioned, the way this textbook is arranged is we introduce the fields, the field quantity in free space, where things are more simplified, and then we understand how matching, having material is going to affect the field. So for the second PowerPoint set, I am going to talk about don't like to have this guy here. Let's drag it. Right? So electrostatics in materials. So before we really go on, we have to understand how materials are classified. Okay. I'm sure all of you have basic knowledge to how materials are classified. You can classify materials due to their density, right? Gas, solid, and liquid. But in electromagnetics, we classify materials based on their ability to conduct electricity. So what does that mean? Well, we know materials are comprised of a lot of atoms, and atoms have electrons, protons, and neutrons, right? So somehow, if I can have a material and I add potential difference, and then I can have conducting current, that means I have a lot of electrons inside this material which can move, okay? So for those material, we call them conductors. Metals are likely good conductors, right? So the materials that can conduct current are called conductors. On the other hand, if you have materials, even though you apply very high potential difference, you still don't have currents. And those are called insulators. They don't conduct current. And the reason is the conduction band, where you have 3 electrons, are very far distance in energy from the valence band. Okay, so you don't really have a lot of electrons in the conduction band for insulators, right? And of course, you have material lying somewhere in the middle, where you add, without applied potential difference, it does not conduct current. But when you apply above certain voltage difference, it starts to conduct current. So those are called semiconductors, like silicon, gallium arsenide. So these are all semiconductors. So in this class, I am not going to cover semiconductor. It is a course on its own. I am going to first describe conductor, metal, and then I'm going to talk about insulators. All right? So metals first, and then insulators. I know some of you are falling asleep, so I want to probably wake you up. So what I plan to do, at least for today, I'm going to talk about static E fields in conductors. And on Wednesday, we can talk about the static E fields in insulators. Insulators are also called dielectrics, 介电材质, dielectrics. So for these 2, I'm going to leave until maybe next week. All right, so we are going to talk about static electric fields in metallic materials, conductors. When you think of conductors, what does the name imply? And actually, I talked about it. If you have a conductor, conducting material means you have a lot of free electrons. So if you apply certain potential difference, you have electric current flowing across the material. So what happens when you have this big battery, which provides a huge potential difference, but then you have a wet chicken. The chicken gets electrified, right? Because chicken is wet, water, you have a lot of water, you become conductive. Don't do this at home, okay? Please don't do it. So why do I choose a wet chicken? because we are in the department of electrical engineering. So if you understand about Chinese, electrical engineering transferred into Chinese, the pronunciation is exactly an electrified chicken. 电机, right? Okay. So be careful when you study in our department, right? Okay. So if I have a piece of good metal, it's a very good conductor, right? There are two basic aspects to a very good conductor. In the future, I'll just call it perfect conductor. If you have a perfect metal, perfect conductor, you have two special aspects. One is inside this metal, you're not allowed to have charge distribution. So this charge density inside the metal has to be 0. That's point 1. Point number 2, inside the metal, you cannot have electric field. Right? So some of the students are extremely naughty. You might be wondering, oh, what happens if I inject charges into the perfect metal? What is going to happen? I can tell you the answer right now, but later on, I will prove it to you. Right? If you have a perfect metal to start with, but you're a naughty student and you purposely inject a lot of free charges into the metal, you want to challenge the fact that the professor told you there cannot be charge inside the metal, so you purposely inject those charges into the metal. What I can tell you is, within a split of a second, much shorter within the blink of your eyes, roughly 10 to the minus 19 second. That means zeptoseconds, 100 zeptoseconds. All the charges will be forced to surface. What does that mean? Even though you inject a lot of charges into the metal, almost instantaneously, all the charges will be forced to swim to the surface of the metal. So that inside the metal, you still don't have charge density. And if you don't have charge density, by Gauss's law, you cannot have electric field intensity distribution. Okay? Later on, I will prove it to you. I can even just show you the time scale. It's really zeptosecond. But up to now, the basic two assumptions for perfect metal are: you cannot have charge inside the metal, you cannot have the field inside the metal. You must be scratching your head, why not? Why not? Why do the charges need to be distributed along the surface but not inside? Well, let me ask you in a very philosophical way. If you have a piece of conductor, a very good conductor, a perfect conductor, what do you think of its potential? You have a piece of perfect conductor. It means Well, the electric potential should be the same everywhere, right? If you have like gold or silver, platinum, you have this solid gold, and you ask yourself the potential at this point, potential at this point, potential at this point, aren't they supposed to be the same? Right? So let me just draw a simple circuit diagram for you. This is something you learned, right? You have a resistor, you have a capacitor, you have an inductor, L, C, R, right? They are somehow connected together at 2 points. So these are conductors, right? Resistors, capacitors, inductors are somehow manufactured, so you have 2 conductors at 2 ends, and you're free to connect them. So if you tell me this point, V1, V2, V3, they are somehow linked together through good or perfect conductors, V1 and V2 and V3 can only be related in one way. They're all equal, right? Because they are the same node. So they can only have one electric potential. That's called voltage. So this is based on our understanding. If you have perfect metal, so inside the metal or everywhere on the metal, it is coming from the same piece. You have the same potential everywhere. Okay? So if any 2 positions are having the same potential, it also implies inside the metal you cannot have field distribution. Why? Can anyone answer this question? It's too bad you're not in classroom. Usually I like to ask a lot of questions. The answer lies directly from our previously covered topic, electric potential. Right? Electric potential, the potential difference between 2 points, P1 and P2, can be derived when you perform the line integration in some kind of field distribution. But now the fact that this has to be 0 everywhere within a perfect metal or conductor, it also implies within the metal you are not allowed to have E fields. Okay? Perfect conductors have the same potential everywhere. So inside the metal, you don't have E field distribution. Once you do, if you do have E field distribution, it means within the metal, point by point, you might have potential difference. But that really contradicts our understanding. Right? So this comes actually first. Inside a good metal, you cannot have allowed field. And then you use Gauss's law. If you cannot have fields, you cannot have charge distribution. All right? So this is the sequential. Based on our understanding, we don't have potential difference. Then we don't have fields. We don't have charges. Okay? So that's exactly what Gauss taught us. So inside, if you don't have field, you don't have charge, right? So now take a close look. We can try to understand this in a more detailed way. If within the metal I have 2 points, and somehow they don't have the same potential. If they don't have the same potential, that means I have E-field distribution. Okay? If I have E-field distribution, I have potential difference. What is going to happen for conductors? Conductors have lots and lots of free electrons. Right? Free electrons mean they're free to move around. So once you have a field distribution, that charge, that free electron, is going to move. Right? So if you have high potential, low potential, your electron is going to move. Okay? And that really violates our basic assumption of static E field. Right? Okay, so in a static condition, let's summarize again. Inside the metal, no charge, no field. But the charges are allowed to locate on the surface of the metal. Alright? Now, take this challenge. Please draw out the resulting electric field lines due to the surface charges. Try to draw out the resulting E field lines. How difficult can that be? Right? You have a metallic surface, you have a charge, right? I still remember the professor taught me, well, if you have a charge, the E field lines are just radiant. Right? It goes out, it goes out, it goes out, like that. How difficult can that be? Well, then you're totally wrong. As I mentioned, if you have a single charge, yes, you will have a radiant E field line. But as we just talked about, when you have two charges, the field lines are dramatically different in geometry. And now you place a charge on top of a perfect metal. That fact is going to change your field distribution dramatically. Right? So think about it. Let's take a close look at only two field lines. This one and this one. Let's forget about all the other field lines. So I have a perfect metal here. I have a single charge here. Let's take a look at the two extreme cases where one of the field line is perpendicular to the metallic surface. The other one is tangent. Okay? So let me just write it. E tangent for this guy, and E normal for this guy. Which one of the two field lines cannot be there? You can only have one. This is tricky, What? You can only have the normal component or the tangential component. If you were forced to choose one, which one would you choose to survive? Any feedback from the students?
No.
No? Anyone watching?
19.
19, yes, okay. Think about it. If you have tangential field line, what does that mean? As we introduced in the previous class, if you have a charge, a positive charge, and you're walking in the direction along the field line, you lose potential, right? So if you have tangential field lines, it means this point is having a higher potential as compared to this point. But they are all on the metallic surface. And that really contradicts to our understanding of perfect conductor. Because we said repeatedly, on any point within the metal, they have the same potential, right? So you're not allowed to have the tangential E field lines. If you have them, you're slapping your face. If you have tangential component, that means, let me just draw this one for you, okay? For example, you have a flat metallic surface, and you have a charge, and you want to argue, yeah, I want to have the tangential field line. Then you're saying V1 and V2 are actually different. So that is not allowed. So for perfect metals, if you have the surface geometry, you know the geometry of your metal, and somehow you have charges, right, spread out on the surface. The only way you can have E-field lines is they all point in the direction perpendicular to the local surface. In other words, all the field directions are parallel to the surface normal. Okay? So only the normal components are allowed. You cannot have the tangential component. Tangential means if you walk along it, you have potential difference, but potential difference appears on the same metal. But if you walk in the direction normal to it, that's fine. You're moving away from the metal. Okay? So I'm introducing this in a more philosophical way. I haven't invoked any math, but I'm just only describing what we understand about conductors. Conductors have equal potential, therefore they cannot have fields inside, they cannot have charge inside, they cannot have tangential field distributions. Even at the surface, it's not allowed. Okay? So, this is coming from curl of E is equal to 0. Right? The integration form is, if you have a closed loop integration of E, it's 0 everywhere, right? If you have a closed loop. So now what happens if you have a conductor and you have another material forming an interface? Conductor, air, you have an interface. So this is to further corroborate you cannot have the tangential field component, even though you have a point charge. Whenever you have the curl operation, you need to form a closed loop, right? So for this case, this true length can be, this delta H can be extremely short, so you don't really need to evaluate its contribution. You only need to evaluate the top segment and the bottom segment, right? So you only have to calculate the line integration of the E field inside the metal along this path C to D, and the E field contribution along A, B segment in air. But as we talked about, fields inside the metal is zero everywhere. So here, you don't have any contribution here. Therefore, you cannot have any contribution from AB. That is telling you, that's confirming, even though you have a charge position at the interface slightly in the air side, you cannot have the tangential component, because by default, curl of E is equal to 0. So at this interface, no field inside the metal, there's absolutely no field. So no tangential field. If you don't have contribution from this segment, you cannot have contribution from this segment. Right? On the other hand, Gauss's law tells us divergence of E is equal to rho divided by epsilon 0. So eventually, yes. If you have a piece of conductor and you have the air, so it forms an interface, at the interface, you can have charges deposited along the surface, and you can have all the field lines emitted perpendicular to the interface. Okay? So in this case, once you know the charge density on the surface of your metal conductor, you know your field strength are all in a normal direction, and its quantity is your charge density divided by epsilon 0. Think about it. What is the difference in this case as compared to our uniform charge plane distribution? This is something we covered, right? If you only had a plane of charge, but it's not a conductor, then you are allowed to have normal E field lines pointing out. Above it, you have fields going up. Below it, you have fields going down. So if you only have the plane of charge distribution, you can have fields up and down, and therefore the magnitude is twice weaker. But in this case, you have perfect conductor, no field can be present within the conductor, but you have charges, so you can only emit the field outward and not into the conductor. Therefore, its strength is twice stronger as compared to a planar charge distribution. Right? So think about it. It's quite unique. Perfect metals are really, really unique. Okay? So I'm adopting a very descriptive method to introduce perfect metals. But somehow I'm linking to the fundamental postulates, right? Curl of E equals to 0. Divergence of E is equal to rho divided by epsilon 0, right? So for that, let me conclude for the day. But for the students, you are going to enjoy, I hope you will enjoy, your first examination next Monday, class time, which means we will start from 10 a.m. for 2 hours. You will cover transmission line and vector analysis, so only 2 topics. This Wednesday, the 3 TAs are going to work for extra hour. So this Wednesday, 8 a.m. I suppose you have received lots of email instructions from the head TA. So she's very responsible. So this Wednesday, 8 a.m., the TAs are going to walk you through the procedure to conduct the online examination. This is the very first time we do it. Due to the virus, we're forced to do it. So please do pay attention to the emails and do participate this Wednesday, 8 a.m. I repeat again, 8 a.m. So please wake up and do make sure you can connect online. You're able to get your examination problems, the fake ones, on Wednesday. Okay? So please pay attention to all the messages from the TA from today until Wednesday. Right? And after you do the practice, please stay and enjoy my real live streaming class. I know on Wednesday only less than 10 students are joining. I'm very lonely. All right, see you Wednesday.